A non-measurable set is a set which cannot be assigned a meaningful Lebesgue measure. I will focus here on one-dimensional sets that are a subset of the real numbers. So measure is analogous to length. Measure is a generalization of length. If we have an interval from A to B, then its length or Lebesgue measure is simply B minus A. Whether the interval is open at one end or closed, it won't matter. So basically all those intervals will have a length or Lebesgue measure B minus A. The measure will be a function that takes a subset of the real numbers and assign to it a value that is non-negative, and also that includes plus infinity. So a measure is greater than or equal to 0, and the measure can be plus infinity. The measure of the empty set is 0. The measure of the whole real axis is plus infinity. Now, if we have sets that are, or subsets of R that are disjoint, so let's say that we have this interval here and another interval there, then from our notion of length, we know that the total length is the sum. So for a measure, we will basically extend this idea and say that if we have disjoint subsets of R, A1, A2, A3, and so on, then the measure of any finite union or countably infinite union will be the sum of measures for disjoint subsets of R. Also, if I have, let's say, some interval, and if I shift that interval by x, okay, so this interval is from A to B, and then I shift it by x, so that we have this interval from A plus x to B plus x, then the length is the same. It's exactly B minus A. So again, it is desired that our Lebesgue measure function will be translation or shift invariant, which means that if we have a set A, which is a subset of R, then A plus X is a translated or shifted version of A. So basically, if A contains elements, what we will do is that to each element in A, we will add X, which means that every element in A will be shifted or translated by the real number X. So it makes sense to impose this condition that we want the measure of the shifted set A plus X to be exactly equal to the measure of A, regardless of the shift X. Now, can we assign? So basically, let's recap. What are the properties that we need from a measure? Again, think of it as a generalization of the concept of length in one dimension. The measure of an interval from A to B is B minus A. The measure of the empty set is 0. The measure of the set of real numbers is plus infinity. The measure is a non-negative real number or plus infinity. The measure of a finite or countably infinite union of subsets of R is the sum of the measures. And then we have this translation invariance property. So this seems plausible and it makes sense. The question now, can we assign a Lebesgue measure satisfying these conditions to every possible subset of R? Okay, and it may seem, why not? Okay, but what have been proved is that there are subsets of R to which you cannot assign a meaningful Lebesgue measure. So to show this, we will need first to discuss a useful partition of the set of real numbers. So let R, written between two square brackets, be the subset of real numbers containing all real numbers whose distance from R is a rational number. Okay. So is this subset of R empty or non-empty? No, it is guaranteed. It is guaranteed to be non-empty. It must be the case that R belongs to this subset of R. Okay, because again, this subset of R, it contains all real numbers such that the difference or the distance from R is a rational number. So the distance between R and itself is 0, and 0 is a rational number. And so basically this subset of R is non-empty. Now, suppose that we have a union of those, guys over R, where R is in the set of real numbers. Note that we are sure of this equality because again each one of those guys contains small r, and so basically this union contains the real numbers. But the question now, if we have two of those subsets of R, how are they related? So we will try to make an argument that these two subsets are either disjoint, so their intersection is empty and there is no common element between them, or they are exactly the same. Or they are exactly the same. So take this subset of R with this A. Again, this will be all real numbers that are separated from A by a rational number. And take B, and this subset of R is the set of all real numbers separated from B by a rational number, and let A and B be distinct. So it may be the case that these two subsets do not intersect. They are disjoint. Okay, so we are done. But what if there is an intersection? So now we will show that if there is an intersection, actually these two guys are the same. So if there is an intersection, then at least there will be a real number, let's call it C, such that C is in this subset of R and C is also in this subset of R. Because of this, A minus C must be a rational number. C is in this subset of R by definition because the difference A minus C or C minus A is some rational number. So let's say that A minus C is Q1, which belongs to the set of rational numbers. And similarly, C minus B is another possibly different rational number, Q2. Now, if we add these two guys, then A minus C plus C minus B is Q1 plus Q2. So if there is an intersection and this intersection contains the real number C, it must be the case that A minus B, the difference between A and B, is a rational number because the sum of two rational numbers is indeed rational. Now we will show that we have these types of inclusions. So take an element in this subset of R with the parameter A. So the difference eta minus A is a rational number. Say it is Q3. Don't forget that we have already established that the difference between A and B is a rational number, which is this Q1 plus Q2. And if we add these two, we get that eta minus B is the sum of these three rational numbers, which is also a rational number. So the distance between eta and B is a rational number. So eta must be in this subset of R parameterized by B. So if you start, so if eta is in this subset of R, then eta is guaranteed to be in this subset of R parameterized by B. Now you can repeat, but now take gamma that is here. Again, same story. It is here by definition because the difference is a rational number. Let's say that it is Q4. And we have already established that A minus B is this rational number. Add the two equations, then A minus gamma is the sum of these three rational numbers, which is a rational number. So gamma is in this subset of R parameterized by A. So you start with an element here, it must be there. And so we have inclusions in both directions, and it must be the case that these two guys are exactly the same. So R can be partitioned into disjoint subsets. Each subset is characterized by the difference between any two elements being a rational number. Okay, so the conclusion is that I can take the set of rational numbers and I can write it as a union of subsets. Basically, in each one of those subsets, what do we have? We have real numbers that are separated from one another by a rational number. So we have subsets here that basically are disjoint, and in each subset, if we have a real number x, then we have x plus every possible rational number. The numbers here, if you take the difference between any two numbers, then you get a rational number. And this is true for the elements in each one of those subsets. Together, they give us the set of real numbers, which is R. How many of those guys do we have? Okay, so now it's like at the beginning I said that R is the union, and I took this R to be in the set of real numbers. But now we have shown that there will be basically subsets here that are exactly the same. So eliminating these, we get this collection here, which I called AV. So it's a collection that is indexed by this index set. How many subsets here that we have whose union will give R? So the claim is that the number of subsets, which will be the cardinality of this index set, must be uncountably infinite. Must be uncountably infinite. And this is because of a rule. So now each one of those guys, so each subset here is countably infinite. Again, you can think of it as a real number, and then you take this real number, and to this real number you add all possible rational numbers, and the rational numbers are countably infinite. So each one of those subsets of R, it has a cardinality Aleph node, which is the cardinality of the set of positive integers, rational numbers, and so on. Now there is a rule that basically if the terms in this union, if the number of terms, if the cardinality of the index set is also countably infinite, then the union is countably infinite. But the union gives us the set of real numbers, which is uncountably infinite. Okay, so the set of real numbers is this small c, the cardinality of the continuum, and this is strictly greater than elif node. So it must be the case, since each subset is countably infinite, it must be the case that the subsets whose union give R, the cardinality of this index set must be uncountably infinite. Now, in each of those subsets, there is a number between 0 and 1. There is a number between 0 and 1. Again, know that each one of those guys is a real number, and you add all possible rational numbers. Okay, so let's basically construct a set, which here I will give it the name S. And so what is the set S? So this is our partition of the set of real numbers. From each one of those subsets, a number will be picked such that this number is living between 0 and 1. So from each one of those guys, from AVs, we will pick a real number. The real number is greater than or equal to 0, less than or equal to 1. So this will be the set S. And then using set S, we will construct another set. And this other set will come by taking set S and shifting it or translating it by all possible rational numbers between -1 and 1. Okay, so again, this is the partition of real numbers. Those are disjoint subsets of R. In each subset of R, in each one, the numbers differ from one another by a rational number. Okay, and of course, this means that if you take a number from this subset and a number from that subset, the difference will be an irrational number. So from each one of those guys, a number is taken that is between 0 and 1. And so we construct our set S, and then we do all shifts or translations of S by rational numbers in the interval from -1 to 1. Okay, so Q is a rational number that is greater than or equal to -1, less than or equal to 1. And then we have basically the union of all those guys. Okay, so this is a construction using this set, which is S. Okay. Now, what is the measure of this union here? What is the measure of this union? Now, to say that the measure of the union is the sum of measures, it must be that those guys are disjoint. And they are disjoint by construction, right? Because if you take elements from each one of those subsets to construct set S, then if, let's say that you shift set S by 1/2, if you shift set S, by 1/2, so you take each element here and add 1/2, then this real number plus 1/2 will be another number that is here by definition, because those all numbers here differ by a rational number. Now, this number, if we add half, it will be some number that is here, again by the way that these subsets of R have been constructed. and so on. Okay, and if you shift by 2/3, then again you will have, if this is the number that is picked and it's a number between 0 and 1, if you add 2/3, which is a rational number between -1 and 1, you will get this number, which is again another guy that is living here. And this one will be here, and so on and so forth. It cannot be the case that we get intersections between these guys. Why? For example, if you take this number, if you add distinct rational numbers, you get this number is different from this one, is different from this one, and so on and so forth. Can this number be the same as this number? Can this number, so this number, we are sure that it's different from this one. You know, here we are adding 1/2, here we are adding 2/3, but you know, perhaps we can have this one equal to this one. Can this be the case? Of course, no, because this is a number that is living here. This is a number that is living there. And the difference between these two numbers is an irrational number by construction. Okay, so if these two guys are equal, then the difference between them is, you know, the difference between 1/2 and 2/3, that's a rational number. But actually this cannot be the case, because this guy is here, this guy is there, and again, those subsets of R are disjoint, and in every subset the numbers differ by a rational number, and if you take a number from here and the number from there, the difference is irrational. So there can be no intersection between those shifted copies of the set S. The implication of this is that we can, you know, say that the Lebesgue measure of the union, because this is a union of disjoint subsets of R, can be written as a summation. Okay, so again, we have R, and we write down the set of real numbers as a disjoint union of subsets. How many of them do we have? We have uncountably infinite number of them. And how are they characterized? You know, here we have numbers that differ by a rational number. If you pick a number here and then another number, they must differ by a rational number. And the same applies to this subset, that subset, and so forth. Now, if you take a number from here, a number from there, they differ by an irrational number, because if they differ by a rational number, then basically, as we proved initially, you know, if two of those guys share an element, then they are exactly the same. So this was basically this proof here, that we have, if A and B are in R, then these are the only two possibilities. So what we do is that we construct set S. We take an element from this here. Okay, what element? You know, the only condition, it must be a real number that is living in the closed interval from 0 to 1. And then we pick a number from here, and then we pick a number from there, and so on. So the construction of set S, you know, is justified by the axiom of choice. Okay, so, you know, how is it possible to actually do this construction? So this construction is justified by the axiom of choice. So now we have this set S, and what we do is that we now form a union of all translated or shifted copies or versions of S, where we shift S by every rational number between -1 and 1. Now, due to the structure of set S and how it is obtained, we will find that those shifted copies, they are disjoint subsets of R. And so if we study the Lebesgue measure of such a union, we can say that the Lebesgue measure of the union is simply the sum of the Lebesgue measures. Now remember that when we talked about what can be a reasonable property of the Lebesgue measure, it was this translation invariance. So if you have a set of elements, all are real numbers, if you take this collection of real numbers and then add to all of them an arbitrary real number, you think that the measure should not change. So this means that the Lebesgue measure of S plus Q, where Q is some real number between -1 and 1, by the translation invariance property, this is the measure of S itself. So now we have a summation, and this summation is, so here we have a countably infinite number of terms. Again, because this summation is over the real numbers between -1 and 1. And now every term is exactly the same. So all these, okay, so let's write it here. So all these terms are equal by translation invariance. Okay. So now what is the sum? There are two possibilities, right? So we said that the measure, the Lebesgue measure, is a non-negative real number or plus infinity. So the measure can be equal to 0, or the measure can be basically a number between 0 and plus infinity. Now, if the measure is 0, then we have here in this summation 0 plus 0 plus 0 plus 0 and so on, so it will be 0. If the measure is greater than 0, any positive number, if the measure is anything here, and then we have an infinite sum, countably infinite number of terms in this sum, then the measure will be plus infinity. So based on the properties imposed on the Lebesgue measure, it must be the case that the measure of this union is either, it depends, it's either 0 or plus infinity. It cannot be anything in between. It's either 0 or plus infinity. Until now, there is no problem in the argument. However, we will get a contradiction. We will now study the problem from another perspective and discover that actually, we cannot have this measure equal to either 0 or plus infinity. How can this be true? Now, our set S is between 0 and 1. So S is not the interval between 0 and 1, but basically it is a bunch of real numbers, actually an uncountably infinite number of real numbers living between 0 and 1. So what do? You shift S. What is the maximum possible shift to the right? Is 1. Okay, and so the maximum you can reach here is 2. And to the left you shift by -1, so the maximum you can reach here is -1. So the shifted copies of S will live between -1 and 2. This union is between -1 and 2. Okay, so this is, again by construction, because set S, it contains numbers just between 0 and 1. You take those numbers and you add to them every rational number between -1 and 1. So the maximum thing is that you add 1 to every number in S. And then, the least number is that you take the numbers in S and subtract 1. So you get something between -1 and 2. Now, if If B is a subset of R that is contained in A, then the measure of A is exactly the measure of this union. I can take set A and say that A is A intersection B union A intersection B complement, right? So A is equal to A intersection B union B complement. So A is A intersection B union A intersection B complement. Now, A intersection B and A intersection B complement. So here we have B, here we have B complement. So these two guys are disjoint. And because they are disjoint and we have a union, then by the properties of the Lebesgue measure, then the measure of the union is the sum of the two measures. So we have a sum here. Now, because B is contained in A, then A intersection B is equal to B. Then this measure is the measure of B. And so what we have here is that the measure of A is equal to the measure of B plus the measure of A intersection B complement. And the measure is non-negative. And so it must be the case that the measure of A is greater than or equal to the measure of B. So this is the rule, that if A is, or here, if B is a subset of A, then the measure of B is less than or equal to the measure of A. So now, since this subset of the set of real numbers, again, because S is between S contains an uncountably infinite real numbers all between 0 and 1, then shifting by the rational numbers between -1 and 1 will basically lead to numbers that are between -1 and 2. Because we have this containment, then the measure of this union is upper bounded by the measure of this interval. This is an interval between -1 and 2. The length of this interval is simply 2 minus -1, that's 3. So it means that the measure is upper bounded by 3. Note that by this argument, the measure is plus infinity or 0. It cannot be plus infinity. It cannot be plus infinity because, now noting that this union is basically is contained in the interval between -1 and 2, then basically the measure of this union is upper bounded by 3. It cannot be plus infinity. Then you may say, well, then it must be the case that the measure is equal to 0. Okay, but this is also not true. Recall that we have the set of real numbers and it is written as this union. Now, the claim is that this union of interest contains every real number in the interval from 0 to 1. Okay. Why is this the case? Pick a number x. Pick a number x. Okay. X is a real number. So because x is a real number, it is living in one of those subsets of R. Let's say that it is living here. X may be equal to the element that that is chosen in the construction of set S. X may be this guy here. Okay. Or it is another element in this subset of R. But if X is another element, then the distance, okay, so the distance between these two guys is a rational number. And note that this is a number between 0 and 1. And X is a number between 0 and 1. So definitely this difference is a rational number between 0 and 1. And so when we take set S and we shift it by all possible rational numbers living between -1 and 1, we simply cover every real number from 0 to 1. So this set here contains the closed set from 0 to 1. Again, take an element from here. Take any element from here. Okay. So the question is this element in S or in any copy of S that is shifted by a rational number between -1 and 1? Well, if you take a number from here, it must be in one of those guys. It can be that this number X is the chosen element in set S. Okay, so it is in S. If it's not in S, well, it is in S plus some rational number, because we construct this union by adding to S, by shifting S or translating it by all possible rational numbers between -1 and 1. And if X is here, then it differs from the chosen element in S by a rational number between -1 and 1, because this number is in 0, in the interval from 0 to 1, and this X is in the interval from 0 to 1. So this contains that. Now we have proven that if B is a subset of A, then the Lebesgue measure of B is less than or equal to the Lebesgue measure of A. Then the Lebesgue measure of the interval from 0 to 1 is a lower bound on the Lebesgue measure of this union. So the Lebesgue measure of this union is greater than or equal to 1. So let's see. So by those arguments, so by the arguments below, the Lebesgue measure of the union is between 1 and 3. So, but by this argument, it is either 0 or plus infinity, not between 1 and 3. And there is no other possibility that we have. We have a contradiction. Because, you know, what is the measure of S? If it's 0, we should get a 0 for the measure of the union. If the measure of S is strictly positive, we should get plus infinity. But actually, we can show that the measure is a number between 1 and 3. So the set S is pathological. It is problematic. It is a non-measurable set. It is a set which is a subset of R to which you cannot assign a meaningful measure that satisfies the properties that we talked about, which seem like these properties seem very reasonable and plausible. So there are subsets of R that are non-measurable, and because of this, you know, in applications, for example, like in probability, if we do probability and the sample space is uncountably infinite, then when we basically choose a sigma algebra, we don't choose the power set of R. So, for example, if our sample space is R, we don't choose our sigma algebra as the power set. Again, because of a problem that is, you know, that is similar to what have been discussed here. We limit ourselves to a certain collection of subsets of R so that we produce consistent and meaningful results.